So, guys, we are now starting chapter 4. The first thing that we're going to do is a section of word problems. It is a really interesting section, but it can be difficult for a lot of students because we're trying to relate rates. And that's actually the name of the section's related rates. So, first thing I want to do is let's talk about what related rates are. So, we've seen that for quantities that are changing over time, the rates at which these quantities change are given by derivatives. If two related rates are changing over time, the rates at which the quantities change are related. For example, if a balloon is being filled with air, both the radius of the balloon and the volume of the balloon are increasing. In this section, we consider several problems in which two or more related quantities are changing, and we study how to determine the relationship between the rates of change of these quantities. So here's where related rate problems get frustrating. It's kind of setting up these problems. So in many real world applications, related quantities are changing with respect to time. Now, everything that we have done up to this point has been in terms of respect to either x, or it's been x. We've done derivative of y with respect to x, but now we're switching it up and we're going to do the derivative with respect to time. So for example, if we consider the balloon example again, we can say that the rate of change in the volume V is related to the rate of change in the radius R. In this case, we say that dV dt and dr dt are related rates because V is related to R. Here we study several examples of related quantities that are changing with respect to time, and we look at how to calculate one rate of a change given another rate of change. So that's kind of what we're doing. Guys, with this section, it's going to be imperative that you are very, very careful with what variables you're using. So you want to pay particular attention to what variables you're using, because if you don't, you're going to get lost. So the next thing I want to do is let's look at the strategy for solving these things. This is a great box to know. This is a great box to refer back to. So our problem solving strategy in terms of solving a related rates problem. So number one, you're going to assign symbols to all variables involved in the problem. Draw a figure if applicable. I do strongly encourage you, if you've got a nice problem that you can draw a picture for, draw it. State in terms of the variables, the information that is given and the rate to be determined. Number three, find an equation relating the variables introduced in step one. Number four, using the chain rule. So we spent last chapter going over the chain rule and how that works. So we got to make sure that we are looking at that. We also spent last chapter looking at this idea of implicit differentiation, which we will be using for this chapter. So using the chain rule, differentiate both sides of the equations found in step 3 with respect to the independent variable. This new equation will relate the derivatives. And then number 4, substitute all known values into the equation from step 4. Then solve for the unknown rate of change. Guys, this process is going to make more sense when we actually get into the word problems. Now, I love this note down below this. So note that when solving a related rates problem, it is crucial not to substitute known values too soon. For example, if the value of a changing quantity is substituted into an equation before both sides of the equation are differentiated, then that quantity will behave as a constant and its derivative will not appear in the new equation. So please be careful. Now, if you'll notice, when I go over this, I'm only going over the highlights needed to solve these problems. I strongly encourage you to read this whole entire section and look at the examples that they are giving. I try to give you more examples to go by. So please make sure that you're doing that. All right, so let's do an example here. The first problem that we are going to look at is number 1. So number 1 is just practicing. So for the following exercises, find the quantities for the given equation. So find dy dt at x equals 1 and y equals x squared plus 3 if dx dt equals 4. So we're just practicing this process. We're not actually setting up a problem here. So let me switch to a whiteboard. So on number 1, they give us x equals 1, y equals x squared plus 3. And they also give us dx dt is equal to 4. So again, one of the biggest things to understand is we are not going to plug anything in too quickly, because when you plug stuff in, you get just numbers, no variables, which means when you take the derivative, they go away. So we want to make sure that we're taking the derivative first. So what I'm going to do, notice how this is in terms of dt. I'm taking the derivative with respect to t. So when I go through and do this, I'm going to take ddt of both sides. So I'm taking ddt of y, because we're doing it with respect to time this go around, and I'm taking ddt of this x cubed plus 3. So when we take the derivative, now remember, if you're taking the derivative with respect to something that is not your variable, so please notice I'm going to be taking the derivative of y and x with respect to t, right? So when we're missing, or when we're not taking it with respect to the particular variable that I have in the problem, you have to make sure that you include like your dy dt or your dx dt. That's from the implicit differentiation section. So here, when I take the derivative of y, I'm going to get 1, but because it wasn't t, I'm going to get a dy dt. And when I take the derivative of x cubed, I'm going to get a 3x squared, but that's going to be dx dt. And then when I take the derivative of 3, I get 0. Why do I keep doing that? That's not a... I keep thinking my 3s are, or my 2s are 3s. I don't know why I'm doing that. I did that in another video, but you guys didn't see it because they didn't get posted. Let me rewrite this. So this is an x squared. So when I take the derivative of x squared, I'm going to get 2x. There we go. Okay. So let's talk about what we've got here. Now, I was asked to solve for dy dt. That's what I'm after. So 1 dy dt is just dy dt. So I feel pretty good about that. But now what I'm going to do is I'm going to plug in with what I know, because I want to know the numerical value of dy dt. So I'm going to have 2. X was 1. And I also know dx dt. Dx dt is 4. So when we multiply this out, we're going to get dy dt equals 8. And that's exactly what they were after there. Okay, so that's that problem. I want to do one more of these types of problems before we move on. So I'm going to clear this out. I'm going to do a new share. And we are going to look at number 3. So same type problem here. Number 3, find dz dt at x comma y equals 1 comma 3 and z squared equals x squared plus y squared if dx dt equals 4 and dy dt equals 3. So now we've got it in terms of 3 variables, right? We got x, y, z, and then we're taking it with respect to time. So I've got to make sure that anytime I take the derivative of these things, I do use the dy dt, dx dt, whatever. Okay. So let me write out what we had here. So number 3, we had the point x comma y equals 1 comma 3. We had z squared equals x squared plus y squared. And then we had dx dt equals 4. And we had with my picture over here, dy dt equals 3. All right. So the first thing that I'm going to do is I'm asked to solve this one for dz dt this go around. And if I leave it the way that it is currently wrote, I'm going to have a 2z if I try to take the derivative of it. So I'm going to do something really interesting. I'm actually going to take my z squared, and I'm going to solve it for z so that I have just a z dz dt. That's what I'm after here. So I'm going to go ahead and take the square root before I take the derivative. So I get z equals the square root of x squared plus y squared, which remember I can write it as x squared plus y squared raised to the 1/2, which means I'm going to use the chain rule here in a moment. Okay, so now I'm going to go through and I'm going to take the DDT of both sides. So when I take the derivative of z, remember I'm going to get 1, which I can just write as dz dt, just like I did with the y. And then when I take the derivative of this other side, now again, I'm going to have to use the chain rule. So here we go. When I take the derivative of the outside, because remember with chain rule, we worked our way outside in. So when I take the derivative of x squared plus y squared to the 1/2, I don't care about the x squared, y squared right now. All I'm going to do is have 1/2, whatever was in parentheses, raised to the negative 1/2. And then I'll fill in what was in the parentheses. All right, so there's that part. And then I need to multiply by the derivative of the inside. So the derivative of the inside, the derivative of x squared is 2x. But because it wasn't in terms of time, it's going to be dx dt. That's where those related rates come in. Plus the derivative of y squared is 2y. But because it's not in terms of time, it's going to be dy dt. So now we've got dz dt equals, and at this point I can go ahead and plug in what I know. So I can go ahead and plug in for x and y, I'm going to use 1 and 3. I'm going to use this, I'm going to use this. So I'm going to have 1/2 times 1 squared plus 3 squared raised to the negative 1/2 times 2x was 1, dx dt was 4, plus 2 times 3 times 3. If you go through and work all of that out, you are going to get, because I'm out of room here, you are going to get 1/2 on the square root of 10 times 26, which is going to give you a grand total of 13 on the square root of 10. So that's the answer for dz dt. All right, guys, in the next video, we'll come back and I'll actually do some examples of word problems. So come on back.